Yeah, thank you very much for the organization of this great workshop with a broad range of topics, and also for inviting me, of course. Yeah. So I will talk about a question that is a bit different from the previous talks we had in the morning, but is, I think, very closely related to one of the talks we had yesterday. So we all know that in quantum optics, we can couple like a single atom very strongly to photons and thereby manipulate the properties of that atom. And I want to ask whether one can extend this to coupling of a whole extended solid in such a way that one can possibly use the vacuum fluctuations of the electromagnetic field to engineer ground state properties or thermodynamic properties of that solid. And as I said, this is something which we have heard about also yesterday in a very nice talk. So it's also a question that has been investigated very extensively theoretically in the last years, and I think it's fair to say that there are many theoretical proposals which do not yet have an experimental realization, and a few experiments which are not all fully understood. So one can think of possible mechanisms. So one thing would be that the photons of the electromagnetic field really mediate interactions. So there are proposals of where you basically replace the phonon in BCS theory by photons. Or you can think of single particle effects where the photons dress the single particle properties of the system, such as you can think that the electrons propagating in the solid get dressed by a photon cloud to become polariton-like particles with a different band structure, or something that would probably have been also a topic for this, the possibility to dress magnetic interactions in a solid by coupling them to the electromagnetic field. So, for example, if you think of, this is a Heisenberg super exchange interaction, so a spin flip usually goes via, something's not working. Well, a spin flip goes via an electronically excited state, intermediate state, and if you place this in a cavity, then it can at the same time involve the exchange of virtual photons and thereby like dress this super exchange interactions. And there are several proposals along these lines. Now, what is specific, of course, about an effect like this is that you really need strong coupling of the photons to the matter on the atomic scale to actually have the possibility to dress the exchange here. And this is what leads me like a general issue here. Like if I think of this cavity in terms of a single mode resonator, then we know that the coupling constant goes down like 1 over the square root of the volume. And if I want to place a whole extended solid there in the thermodynamic limit, then that means that this rules out at first sight all these strong coupling single particle effects and leaves us with collective effects that really depend only on the density. And so on the path to the thermodynamic limit, we can ask like either it's really possible to use these collective effects, like the coupling of a photon mode to collective modes in the solid to affect the thermodynamics along the lines of condensation of light matter hybrid modes. Now it works again. Or we really have to think completely differently and acknowledge that once we go to the thermodynamic limit and build a cavity that can actually host the material, it's also an extended cavity. So something like a coplanar cavity, which would then carry modes that also have a in-plane wave vector, so a whole continuum of modes. And we have to understand like how these effects like survive when we couple to a continuum of modes. And so what I will do in this talk, I will actually start from this side here, address the question whether we can to what extent is possible, and more or less end up in this second mechanism. So the collective coupling is probably very well known. So the minimal model for this is the Dicke model, where you have like individual two-level systems that couple to one mode of the electromagnetic field. So these are the two-level systems. The mode here I write in terms of its quadratures, and there's just a linear coupling of the displacement operator, which can correspond to the electric field here to all of these dipoles. And the overall coupling is scales down with 1 over volume. And then we know that if we, in this model, take the number of dipoles large and the volume large such that the density is fixed, we can exactly solve the response of this in terms of a collective coordinate, which is like the superposition of all these dipoles. And in this terms of this collective coordinate, is a two-coupled oscillator, one with the frequency here of this two-level atom and one with the cavity, and the linear coupling, and this linear coupling now scales with the density. Yeah? And therefore, if you solve the like eigennormal modes of this, you get really a splitting, which is controlled by this collective Rabi splitting. And so, as was emphasized also yesterday, since this coupling here really goes with the density, we can, in a solid, can come up with situations in which relatively easily, okay, this shouldn't be said easily, you can reach really ultra-strong collective coupling. And there's also, I can also illustrate this here with a theoretical simulation. It's not by us, but by others. But here, this is a simulation for really a microscopic model, Hubbard model for a correlated insulator, organic insulator with realistic parameters for this organic material, where the dipole is more or less an interband transition, and you can realistically drive this to situations in which you really observe a large Rabi splitting. Now, of course, one also has to acknowledge that some of these effects have a classical explanation, because the same thing I could obtain by, say, I take the conductivity of my material outside of the cavity, or like the dielectric response of the material outside of the cavity, which I can like calculate or measure, and then I solve a classical macroscopic Maxwell equation to get the response, and I would get precisely this Rabi splitting, yeah? Which comes from two coupled oscillators. So in some sense, the collective Rabi splitting, which we see here, is not always necessarily like an indication that we have really a ground state light matter hybrid, yeah? And this is true unless, of course, one of these modes would condense. And it's a question of like superradiance that also has been addressed yesterday. Because in this simple Dicke model, with the linear coupling here, if I just drive the coupling larger and larger, then eventually one of these normal modes would go to zero, and this indicates the instability of the system, which means that beyond this instability, the photon operator would get a finite expectation value, which is why this has been called super-radiant transition, which maybe is a bit unfortunate name because it's an equilibrium state. It has nothing to do with radiance. So one could also look on this from the matter side, where really the dipoles get a finite expectation value, which means they get polarized, which means this is a ferroelectric transition. Yeah? And then, as we have heard yesterday, this proposed instability has been challenged. One way to formulate is that one should always formulate this light-matter interaction in a positive definite way. I mean, I have here the x squared term from the cavity, the linear coupling. I should supplement this by another term which comes from the q squared from the matter mode here, such that the terms together give a positive definite coupling. And the argument for this is that eventually something like this is derived by just unitary transformations from the minimal coupling Hamiltonian, which is also positive definite. So you would always retain something that's positive definite. So then if you solve this with the normal mode with this positive definite coupling, of course you get no instability anymore, and this is the absence of this phase transition. And the discussion has come up again. Like in the solids, there are proposals for superradiance in solids, which basically map to a variant of this Dicke model, and no-go theorems and statement that's, again, challenge this no-go theorem. So what I will now show that, indeed, in this situation, we can also, in a microscopic model, I can show you that the coupling to this electromagnetic field can indeed affect this condensation of this mode. However, if I take into account the whole continuum of modes in this case. So let me check time. Yeah. So the minimal model which I'm looking at is could be viewed as a model for an ionic solid, where in each unit cell I have an ion which can take two places. So that's my two-level system with two states plus and minus in the tunneling. And then I assume that there's an interaction between these. This tries to align all these. So this is an easing type interaction, and the whole thing is therefore more or less a transverse field easing model. If you look at the phase diagram of this at zero temperature, and you just need a certain minimal strength of this interaction to overcome the effect of the tunneling, and to drive the system into a ferroelectric phase without the cavity. And so there's this region where the ground state remains not ferroelectric, disordered, because of the tunneling. That is sometimes called the quantum paraelectric state. And you can also see this when you calculate the response function, which I will look at later. For example, along this line here, it's a function of temperature. High temperature, it seems to diverge, indicating like the system wants to order, but then it settles off because the ordering is suppressed by these quantum fluctuations. You could also look at the collective mode, which I'm only sketching here. Like this would go down, would look like it's condensing, but then it also here does not condense. There's also material which falls into this class, strontium titanate, but maybe not. Maybe yeah. So now I'm taking this solid, or this model here, and coupling it really to a continuum of modes. Here, for the moment, you can really think of modes that have like an in-plane wave vector here, and the coupling should be just a linear coupling where the electric field at one point in space couples to like the dipolar transition at that point in space. And then I can take the electric field operator and expand it in terms of the modes here. And there's the coupling constant, which is then the relevant coupling constant here, which will be controlled by two things. One, of course, the shape of the mode functions in the transverse direction, and the other thing, an overall coupling constant, which is basically just the dipolar transition strength of my atoms here. Now, for the later simulations that I show, the parameters can be actually nicely related to also this strontium titanate, because you can simply take this model as it is and use it to compute the dielectric constant, like in the mean field theory, and then the coupling strength is really, this overall coupling strength is also which determines the dielectric constant. So we basically take parameters for this system such that the response dielectric function would fit this typical quantum paraelectric behavior. And then the third term here, that's important, you have this light matter, the modes here, you have the linear coupling, you have to supplement it with a quadratic term such that, again, the combination of these three terms here is a positive definite Hamiltonian. Yeah? And that looks like a dipole-dipole interaction, but it's really part of the interaction with the transverse electromagnetic field that has to be taken into account to make it positive definite. So now how to solve this model? You can approach it by eliminating the photons, and then this gives you an induced interaction, which of course is retarded, therefore depends on frequency. And one thing you can say immediately about this is that at low frequency it will go like omega squared, because it's an interaction which comes from the transverse electromagnetic field, so it's a current-current interaction, which I'm writing in terms of dipoles and or polarization, and the polarization is a time derivative of the current, so it should be omega squared. You can also see it by, in this minimal model, there is the one static part of it, which basically comes from this term which I have to add to make it positive definite, one term which comes from eliminating the photon, which looks precisely like a phonon-mediated interaction in BCS theory, just the phonon being replaced by the photon. And these two in the zero frequency limit exactly cancel, as it should be, and give this omega squared behavior. So that means that if I take the static limit of this interaction, and that's the key point, there's just zero effect. Yeah? Which means I cannot understand the effect of this cavity on this transition in terms of a static mean field theory that we like to do. Yeah? That's the main message. And this is a consequence of what in other contexts of this no-go theorem, if you like. Yeah? Nevertheless, there is a, if you go beyond this mean field theory, there can be an effect, and this is what I will show in the microscopic simulation, but this is something which also is understood phenomenologically by a nice work here by also Eugene Demmler, and I try to summarize this very quickly. Hope not to distort it too much. So the phase transition is related to the condensation of this mode, of this collective mode in the solid. Now, if we would hybridize this collective mode with the cavity, I can kind of shift it. But the key thing is I cannot shift it in the vicinity of where it becomes zero frequency, just because of this effect here, that the effective interaction on this mode vanishes if we go to zero frequency. But what does happen is that this is actually not just the linear mixing of two modes, but like this Q equals 0 condensing mode interacts with like fluctuating modes at all length scales, and this renormalizes this mode down here. And now the cavity affects all these modes at all length scales because they lie at higher frequencies, and this would renormalize the mode in the cavity, but these two effects are different. So this is the effect of the cavity. So the combination of like nonlinearity in the system and the cavity affecting physics at all length scales is what actually saves us here. So now, as I said, we are using a microscopic solution of this model, and I will just not go into detail of this because that's not the right platform for this. Just mention that we have spins which actually interact with a like retarded interaction that includes here both like this near field interaction and also the induced interaction. And this is an interacting model. So to deal with this, we can actually reintroduce a field that mediates this interaction. And then if I view this from a perspective of this field, it's like a harmonic theory for the field that mediates this interaction. And this field locally interacts with the atoms. So if I would eliminate the atoms in my mind, I would get a local nonlinearity. So that means I have a field with a harmonic theory with a local nonlinearity. And this is something which we address by the so-called dynamical mean field mechanism, which actually maps this lattice model onto a collection of atoms which are kind of feel an environment that's self-consistently determined by the rest of the lattice. This single-site model actually also has a nice physical meaning because it's really one emitter embedded in a bath of modes. So it's really the same model which you would have to solve if you go for waveguide, quantum strong coupling waveguide, quantum electrodynamics. We have one like emitter sitting in a continuum. And the way we are solving this is with a diagrammatic Monte Carlo method. Anyway, so I'm here a bit, I'm running probably short in time. Let's see. So this is. 7 minutes before I stand up. Yeah, I think I'm probably not too much behind this time. Yeah. So now the next question is, of course, how large is this induced interaction? How large is the effect from the cavity? And here's I think the biggest challenge in this business is like if I want to look at the induced interaction that's mediated by all these modes, like for example, if I look at the interaction in real space, I have to sum up here this interaction over all modes, and these would be the modes in the cavity. But of course, I have to make sure that I sum up only the effect of the cavity, which is different from the free space. Yeah, so I should only look at the interaction at the part of the modes here which are actually affected by the cavity. And these are the modes below a scale that's set here by the base frequency and is therefore in a phase space that is much smaller than like the number of cells which I have in the lattice. So this phase space factor telling me that the number of modes which actually effectively contribute to the physics here is much smaller than the number of atoms which I have. This is what is the reason why this induced interaction in a normal situation would be small. And what we have to achieve is to couple efficiently like a large range, the mode here over a large range of momenta. And the way we explore this here is to look at the setting in which this mode is actually a surface plasmon mode, so a mode which is like located or located at an interface between metal and the electric. And in this interface, you can have a mode which, as I said, is localized here. It has a dispersion for large momenta, which is flat. And the localization length, like at large momenta, of course, is going down with momentum, as dictated by Maxwell equation. And that means we can have a setting in which we place our 2D material here close to the surface with a certain distance. And then since all the mode functions here decay exponentially at large q, by this distance we can more or less control over what range in momentum space we couple the material effectively to this mode. And this is just two pictures for these mode functions in the Brillouin zone, like by just tuning the distance, we tune the range here, and you really have to go to atomically small distances in the end in order to achieve a wide range of couplings. So this is the setting which we then solve, and this can be probably summarized quickly what comes out. We solve this, as I said, with this dynamical mean field theory. And if we have a system, if we solve this without the cavity, which would mean basically I'm placing it very far from the surface, then I show here again the susceptibility, or rather the inverse susceptibility along this line. So this means this goes towards increasing, so divergent, but then here it softens. And then if I bring it closer to the interface, really I effectively enhance the coupling here, and this would be the distance in units of the lattice spacing of my material. So it's already very close, and but if you go atomically close, you can in this case enhance the interaction sufficiently to really condense the mode in this case. So it's really a situation where we show that this microscopic model in which we show that this coupling to the continuum actually overcomes kind of this no-go theorem, if you like, and helps to condense this ferroelectric mode. So I think I have maybe 3 more minutes, and I wanted to say a few words because everything was very theoretical, and I think in this field there are also few experiments, apart from nice ones which we have yesterday, but there is another experiment which was recently put up, in which I think is a very nice work here from the group of Daniele Fausti. And this is really something which I would say is not fully understood, but it's very intriguing results. And they actually built a really coplanar cavity with 2 mirrors, yeah? And they put in the middle, and this is in the gigahertz to terahertz range, so this is really millimeter distance. In the middle, they put a material, which is tantal disulfide, and this is a rather complicated beast, which shows a first-order metal insulator transition. When this first-order metal insulator transition, you can also detect optically, so without contact, and then you can scan the temperature, and you find really a hysteresis here between these 2 phases. Yeah? The low temperature phase is insulating. It also has a commensurate charge density wave. The high temperature is a, I would say, unusual metallic phase. And then when they put this in the cavity, this transition shifts by tenths of Kelvin. Yeah, so really by a large effect. And you can control this shift both by changing the frequency of the cavity, so by changing the distance of the mirrors, and also by changing the quality factor of this cavity by misaligning the mirrors. Yeah? And this is kind of probably the more remarkable effect, even that like just by misaligning the 2 mirrors slightly, this phase transition shifts. So what would be explanation here? This is a first order transition. Yeah? So you would think the thermodynamics is that at some point the free energy of the metallic phase here becomes lower than the free energy of the insulating phase. So one thing which could happen here, which you could phenomenologically explain this, is saying that the cavity actually selectively couples stronger to one of the 2 phases, therefore modifies the free energy of that phase downward, and therefore shifts the transition. Yeah? Now, of course, you would have to estimate this effect. And the nice thing here, this is something that can already happen on the level of just the linear hybridization of the modes, because the metal will have like some range of low energy electromagnetically active modes here, and which couple to the cavity mode. And they're all in a range in which all these modes are thermally activated. And if the cavity then shifts around the base frequency here, then the spectrum of these modes will change, and therefore their occupation, therefore their free energy will change. And based on this linear theory, you can actually make an estimate, because all you need on the level of a linear theory is the dielectric response function of the material, and this would suffice to also calculate or predict the change of the free energy. The problem, of course, is that there's again this phase space issue. Like each mode of the cavity here, per se, will only contribute like a sub-extensive correction to the free energy, and only the summation over the whole continuum actually gives extensive quantity in thermodynamics. So if you go to that estimate simply, you would find that probably here it's too small, but nevertheless, I think the mechanism per se, since it's a generic mechanism at the first order phase transition, will be something to think about. And then there's a second mechanism. Yeah, okay, I'm almost finished, which is basically describing this as a non-equilibrium system, where like the cavity, like the system here, also couples to like the vacuum, for like photon vacuum, which is the elevated temperature. And what the cavity does is actually restructuring the density of states of the vacuum in such a way that it possibly decouples like the relevant modes in the solid from this vacuum, and therefore redistributes the thermal like load in the material. But this is just another mechanism. Let me summarize. I showed you basically some mechanism here where coupling to a continuum of modes can help the condensation of a ferroelectric transition. I showed you this experiment, which I think is very nice, still needs to be understood. And I, of course, want to thank the collaborators, in particular Katharina Lenk, the PhD student in Hamburg now, who did all the work on the ferroelectric, and also the group of Daniele Fausti, with whom we have discussed this experiment. So, thank you.